We're going to start chapter 6. And it's about continuous probability distributions. Remember, the last chapter was about discrete probability distributions, right? This chapter we're going to see continuous probability distribution, and the difference is that the variables takes continuous values. So the variables in a continuous variable, the value that the variable can take is, any value in an interval. Okay? Like what? Like time, distance, area, weight, and so on. So these variables are continuous variables because it can take any value in a continuum. Now, in discrete probability distribution, the height of the distribution in a continuous. The height of the distributions were the probabilities, right? This is x, this is probability of x, or this is a function of the variable x, and these were the probabilities, right? Whatever the probabilities were. That's in a continuous. This is a discrete, I'm sorry. In a continuous probability distribution, no matter what is the shape of the distribution, whatever shape it is, okay, the areas are measured using areas. It's not the height of the distribution that is important in this, in the continuous. For example, what is the probability if it is 3? What is the probability that x is less or equal than 3? This is the probability, is the area to the left. This is the probability that x is less or equal than 3. You see? It's the area. It's not the height of the distribution. It's not f of x important anymore. What is the probability? Let's say that this is 5. That the probability that x is greater or equal than 5. Now is this the probability? Okay? Because it's the area. And in any distribution, no matter what the shape is, all the area under the curve has to be equal to what? To 1. Exactly. So this is x, this is f of x, which in this case, the f of x is only the height of the distribution, but it's not important for calculating probabilities. Okay? And the area under the curve has to be equal to 1 because that's the way it is. And basically, if I tell you what is the probability that x is equal to small x is equal to 0, that a continuous variable that is exactly equal to a particular value, and then what is the probability that x is equal to 4? Is there any area over here in this line? It's not area. So the probability that x is equal to 4 is equal to 0. The probability that any continuous distribution is equal to one particular number is equal to 0. Okay? Because probabilities are measured by area, and there is no area in one point. If you understand that particular concept, the rest is pretty easy. You need to know continuous probabilities are measured by areas. Probabilities are measured by area. The area in one particular point is 0. Okay? And that's it. That is probably the most important part of continuous probability distribution. Now, in this chapter, we are going to cover three probability distributions. The normal, the exponential, and the uniform. So these are the shapes of the distributions that we are going to cover. So what is the area on this, under the curve on this probability, or in this distribution? What is the area? Over here. 1. What is the area over here? 1. What is the area over here? 1. I mean, it really doesn't matter. This area is equal to 1, this area is equal to 1, and this area, all of them are equal to 1. So in every probability, continuous probability distribution, the area under the curve is equal to 1. Okay. The first one, and probably the most important continuous probability distribution that there is in statistics, is the normal probability distribution. Why it is so important? Because the rest of the book, and this class, and the quantitative management, these and the other class are going to use the normal distribution. So this is probably the most important class from now on. If you understand the normal distribution, it's going to be pretty easy the rest of the semester. Why is the normal distribution? Okay, what is the normal distribution? The normal distribution is a bell-shaped distribution, okay, which is symmetrical, okay? What is in the right side is in the left side, so it's like seeing it in a mirror. It's exactly the same. Okay. Of course, what is the area? 1. Okay. So what is this area over here? 0.5. Exactly, because it's symmetrical. It's exactly symmetrical. You are watching distribution in a mirror. The mean is mu, and the standard deviation is sigma. So it's symmetrical, has a bell shape. And why is this distribution so important in statistics? I mean, think about it. And as you can see, the majority of the values of the distributions are in the middle. Like if I ask you, what is your age? You're going to say 22, 23, 21, 23, 21, 23, 21, 20, 23. There has been someone probably that is 20 or at 19, and there might be someone that is 27, you know. But the majority is in the middle. And that happens probably in most of the phenomena in social sciences. The majority are in the middle. So that's why this distribution is so important, because many of the phenomena that happen has this distribution. Okay? Now, but this is the normal distribution. One type of normal distribution is what is called the standard normal distribution. The standard normal distribution. Standard normal distribution. The standard normal distribution is a normal distribution, of course, but the mean is equal to 0 and sigma is equal to 1. That's it. So it's a normal distribution, but the mean is equal to 0. So this value over here is equal to 0. And the standard deviation is equal to 1. And why is this standard normal deviation so important? Because we don't have tables for this distribution with a mean equal to mu and standard deviation equal to sigma. But we do have tables for the standard normal distribution. Okay? Now, these values over here are negative and these values are positive, right? Because this is 0. So these below 0 are negative values, and this is called the z. This is called x. The standard normal distribution always you refer it as a z. And so we have tables for this. We have tables for this. And that is why it's so important, the standard normal distribution. Now, how are we going to translate a normal distribution into a standard normal distribution in order to calculate probabilities? I mean, we don't have tables for this distribution, but we do have tables for this distribution. Okay, so if I have something in my problem that has a mu and has a sigma, which is not 0 and 1, how am I going to calculate these probabilities over here? We need to translate this distribution into this distribution and then work on this one to calculate probabilities. What I'm saying is, I'm going to raise this. We need to find a way in which we can translate a regular normal distribution into a standard normal distribution, and that is one simple. This is z and this is x formula. And probably this is the only formula that I'm going to require you to memorize, because this is the only formula that you need to memorize. X minus mu divided by sigma. Z is equal to x minus mu divided by sigma. You need to dream about that formula. And this is the way you can translate from this one that is x into this one that is the z. So z is equal to x, whatever x we are dealing with, minus mu, this mu, divided by sigma, this sigma, and then we are going to have this one. Voila. That's it. That's it. For example, and this is an example that comes in your book, I don't remember very well, but they said that phone calls has a mean of 12 and standard deviation equal to 3. Yeah, okay? This and the phone calls are normally distributed with this mean and this standard deviation, and they want to know what is the probability that the next call is less or equal than 40. The next call is less or equal than 14 minutes. So the mean is 12 minutes, the call is 12 minutes, the mean, and the standard deviation 3 minutes. So what is the probability that x is less or equal than 14? And that's in your book again. So they want to know what is the probability. This is what we are dealing with, right? So we have a normal distribution. That the mean is equal to what? To 12. And sigma is equal to what? 3. Okay? So we need to translate this one into a standard normal distribution with mean is equal to 0 and sigma is equal to 1. And we are going to use, and we want to find out what? What is this probability? This is 14. And I want to know this probability. What is the probability that the next phone call is going to be 14 minutes or less? So this is 12, this is 14. Okay? This is what the problem is asking me. But there is no table for this one. So I need to translate this one into a standard normal distribution Z, and I'm going to use the formula C is equal to x minus mu divided by sigma. What is the x value that I'm looking for? 14. 14 minus 12 divided by 3 is 2/3. Okay? 2/3. 0.67. So 0.67, of course, is positive, so it's in the right side of the standard normal distribution, as it should be. It's 0.67. So this area over here is exactly this area over here. So these two areas are exactly the same. Exactly. So the probability that x is less or equal than 14 is equal to the probability that z is less or equal than 0.67. Is exactly. Remember, z is the standard normal distribution. Z is how we call the standard normal distribution. Okay? So the probability that in this distribution, with mean is equal to 12 and sigma is equal to 3, the probability that x is less or equal than 14 is exactly equal to the probability that in the standard normal distribution, the probability that z is less or equal than 0.67. How we get the 0.67? Using the formula that I asked you to memorize. Again, this is the only thing that you need to memorize in this class. You see? Then it's easy. Why? Because we do have tables for the standard normal distribution. Where are those tables? In your book. Those are on page 858, 859. Okay, guys. What you are going to see in your book is 2 pages. The left side is the negative numbers. As you can see over here, in this margin, you're going to be negative numbers. The right side is for positive numbers. Indeed, if you realize the value on the standard normal distribution, which value is equal to 0, the area is 0.5. Why? Because these tables gives you the left side of the distribution. Okay? So this number is the integer number plus 1 decimal position. The second decimal position is in the upper side of the table. So let me refer again. This is the integer part with the first decimal position. The second decimal position is on top of the distribution, right here. You're going to see 0.00, 0.01, 0.02, 0.03, up until 0.09. This is the second decimal position. Okay? So if I want to find the 0.67, okay, what I'm going to look is in the right side. Why? Because it's a positive number. It has to go to in the right side. 0.67. So I have to look the 0.6 and then the 7 and then see what that number is. 0.06 and then below the 0.07. And that is the probability that the z is less or equal than 0.67. And that number is 0.67, 0.7486. Did you see it? Did you see it in your book? The point 67 is 0.7486 because it's 0.6 and below the 0.07 because this is the second decimal position. 0.7486. And that is the answer. The probability, and this is 0.7486. The probability that the next call is less or equal than 14 minutes is equal 0.7486. So this is the answer. What if I ask you, under the same distribution, what is the probability that the phone will last more than 14 minutes? What is the probability that X is greater or equal than 14? Guys, this greater or equal is, it's greater or greater or equal is exactly the same result. I put greater or equal because it's easier. But remember that the equal part has no value. Okay, now, what is the probability that X is greater or equal than 14? I'm looking for the right side. What I'm looking now is, if this is the distribution and this sigma is equal to 3, what is the probability that the call will last more than 14 minutes? How you do that? The whole stuff is equal to 1. So, and I know that this is equal to 0.7486. What is this one? 1 minus 0.7486. Right? So, it's pretty easy. It's pretty simple. 1 minus 0.7486. This is 0.2514. So the probability that X is greater or equal than 14 in this distribution is equal to 0.2514. That's it. Now, let me give you hints on how to calculate probabilities using the tables. And this is going to be used for any continuous probability distribution, okay? But let's say that for standard normal distribution, if I ask you, what is the probability that X is less or equal than a particular number, whatever it is, that distribution comes directly from the table. Okay, if I ask you what is the probability that X is greater or equal, and this number can be in the left side, in the right side. It really doesn't matter where this number is. It really doesn't matter at all. It can be this one, in the right side or in the left side of the distribution. It doesn't matter. This is 1 minus what is in the table. Why? Why? Because the tables give you the left part of the distribution. So the right part has to be 1 minus what is in the table. What if I ask you, what is the probability that is between a particular interval, A and B, wherever A and B can be both on the left side, both on the right side, one on the left side, one on the right side, it doesn't matter. Okay? Doesn't matter where the position of this A and B. Okay? And this one is what is in the table for B minus what is in the table for A. You see? That's how you calculate the interval. I mean, what is in the middle? What is the probability that the call will last between 11 and 14 minutes? Then you have to do this. Is the interval. Okay, this has to be in your cheat sheet. If you want, I can do the cheat sheet for you. I don't mind at all. Or I can put it on in front, and don't have anything with you except right now in the next test you can have the standard normal distribution tables. Okay? And that's it.